My name is Reem Abukmeil, and I'm a PhD student from the Department of Engineering at the Faculty of Agriculture under the lab of the Applied Intelligent Engineering Systems Research Group, and the supervisor is Ahmad Malahi. And today I'm going to give the presentation about the empirical approach to estimate phosphorus in potato plants using foliar spectroscopy. As a general background here, I'm not sure about how much you know about the potatoes, but potatoes are considered the largest vegetable crop here in Canada, and it accounts around 28% of all vegetable receipts in Canada and 16% of all the horticultural receipts here. And the New Brunswick is one of the provinces here in Canada, and it's very well known for the potato production. However, as you can see here, within the years, the production are not increasing, and that was the reason we were approached by the farmers, and they are willing to improve the production of potatoes using more advanced technology, as far as they use the traditional farming until now in terms of estimating the nutrients and the nutrient deficiency for potato plants. And it's very well known now in the recent years, the approach of near spectroscopy and the sensors are well adapted or deployed in the market, especially that they found in the research there is direct correlation between the visible range and near infrared range with the physiology of the plants, how much the plants are suffering or how much are the nutrients in the plants are already reflected by the light. And based on that, many of these sensors are already in the market, but all of these sensors are deployed only for nitrogen specifically. However, for the phosphorus, no sensors in the market dealing with the phosphorus. And phosphorus is considered one of the macronutrient for a plant production. So the presentation of today aims to represent the results and to find the correlation between the phosphorus concentration in potato plant petioles and the foliar spectral reflectance, and to maximize the variation in data points by doing some indoor experiments and beside the outdoor farming and data collection from the outdoor. And for that, we aim to maximize the variation of our data sets for our machine learning and model development. So I just mentioned quickly the petiole in my objectives, and I'm going to explain what is the petiole specifically. So the current approach by all the research ongoing these days, using the spectroscopy or the light reflectance of the leaves based on the chemical content of any of the plant tissues. So the current method, they just take this leaf, as you can see here. They get this leaf, they send it to the lab for chemical analysis, and they consider this as the ground truth. At the same time, they got these leaves for spectral analysis, and they develop the data sets between these chemical analysis and the spectral analysis. And after they develop the data sets, they perform the modeling and machine learning, and they found the correlation between the wavebands, specific wavebands, and with that specific nutrient. And however, the deployment of this method in potatoes are not applicable, especially that the main plant tissue in potatoes is not leaves. So what the farmers are doing now, they got the petiole, and the petiole is this part of the plant, and specifically they take one specific petiole, the fourth from the top. They got it for chemical analysis and not the leaves. So our research is to get this petiole, this one, as you can see, this piece, and send it for the lab chemical testing. And we got also the leaf for spectral analysis. This part is not done by farmers nowadays. They only follow this traditional approach. And we took in total 40 data points from the farm in New Brunswick, Canada. And also we performed our indoor farming, and we control the light and the heat. And we also control the application for fertilizer. And basically, as I just mentioned in the objective, we aim to maximize the variation in our data sets. And we implemented this indoor in our faculty, Department of Engineering, Faculty of Agriculture at DAL University. So we started this. I'm just giving a short of how we receive the results from the lab and how we receive the results from the spectral analysis. So here we receive it from the lab, the chemical results, as you can see, from the phosphorus. And here the type of the data we got from using the spectrophotometer. And maybe I forgot to mention that we are covering the whole, the full range, the range from the visible to near infrared spectral wave bands from 400 to 2500 nanometer. And the skip, as you can see here, every 0.5 nanometer. So this is the shape of the reflectance we got. And this is the chemical results we got from the betiol. And we merge both of them to develop our data set. And the main assumption of this part of our research is we assume a linearity between this kind of results, and this is the chemical results and the spectral data, and we call this is the predictors, and this is the predictors, and this is the responses. And we implemented this equation to develop our data set. And after we developed our data sets, we ran the model. And lasso regression is one of the well-known chemometric machine learning methods that could merge the relationship between the spectral data and the chemical results. And we specifically use or decided to use this regression because, as you can see, we have like from 400 to 2500 nanometer, we have a whole bunch of spectral data, but we have a limited number of sample size. And the beauty of this algorithm, it could just discard the unnecessary wave bands and keep the most significant one to be compared with the to be modeled with the chemical results. And after we implemented this algorithm, we went for the tenfold cross-validation. And to evaluate the performance of our model, we decided two basic parameters. Also, they are well-known parameters to decide the accuracy of our models. The first one is the coefficient of determination. We call it as the R square. And the second one is the RBD, is the ratio between the standard error to standard deviation. The higher it is, the best it is, because it means that the standard deviation is lower between the data points, which is the thing that we are looking for. Okay, it's not moving anymore, sorry. Here we go.
I think if you can move to wrap up very quickly, that'd be great.
Sure. So here are the results. As you can see, the black line is the baseline that we want to be the estimation of our models. And you see the two lines, the blue line and the red line here. And the blue line is only for the data points taken from the outdoor farms, while the red line, the estimation models by the merging the outdoor data points and the indoor data points. And quickly, as you notice, the red line is the closer to the black line, which we confirm the increasing the variation of data sets is very important for model performance. It means that we need to maximize the concentration of phosphorus and not only depending on the outdoor farming, because they only use the standard application of fertilizer. And based on the model, running our model views.
So I think we have to cut you off.